to show you this screen. Good, so here we are. So last time we talked a bit, and then we had the possibility to start discussing this biochemical cycling stuff. We focus more on sustainability definition and the fact that Earth planet is far from a thermodynamical equilibrium system, and the planet is threatened by a number of pressures, so we have to be aware that we need to pay attention on what we do and our impact into the ecosystem. And then we start to talk about, let me see where I can arrange my screen, like this. Yeah. And then we start to talk a bit about deterministic model, and we say that the basic idea is that you get a system and the rest of the universe, and through the boundaries of your system, you may have fluxes of matter and energy, and these flux of matter and energy somehow keep the system out of equilibrium for the ecosystem functioning and define the evolution of your system. Now, if you want to somehow describe this dynamic with numerical models, you have the possibility to use different type of model, but pretty often the model that we use in biogeochemical cycling is deterministic model, meaning that you get a number of state variables within your system that define exactly the state of the system and also the evolution of the system. And so we say, let's say that your system is defined by a state vector of n components, then you will get the possibility to define the evolution from time t to time plus 1 as a function of the state variable and the boundary condition. And the boundary condition, in our case, somehow drive the system and keep it far from its thermodynamical equilibrium. And then it may be the case that you get variables that you're interested in that are not state variable, they are not part of your system, they are not X, but they are some post-processes that you can derive from the state variable of your system. Good. These may be discrete in time because you move from t to t plus 1, or they may be continuous in time. Good. So we say that your system would be a number of state variable, and you want to be able to get a function for x of your variable. And these energy fluxes are your boundary condition. Then we talk about the origin of the element, and we saw that at the macro scale, everything starts with the Big Bang, and then the stars, and then more heavy elements that are produced later on. And we saw that there is this zigzag situation, which is due to the fact that even elements are more stable than odd element. We talk about pressure, temperature, and a bit also on this generation of movement. So we saw that there is this regional difference in the energy density that reach the planet, so that here, close to the pole, the same amount of energy, because those are parallel rays, is diluted over a large area, while in this situation, the same amount of energy is, let's say, less diluted. So here you get higher energy surplus. Here you get lower energy surplus. So here you get higher temperature, and here you get lower temperature, and the difference in temperature drive here movement of air, because here you get very high temperature and you get air that became less dense and go up, and this calls some air from the lower temperature region, and this fuel those cells in the atmosphere that we call Hadley cell. Here again, the Hadley cell, same stuff. That would be this one. But since you get Earth rotation rather than parallel line, you get arcs. And those arcs are the wind rates. Great? And this is the atmosphere. And then in the ocean, it will be a different stories, but we will get to that in a different moment. And since you get the tilt between the north-south pole and the axis, you also get season, so that in the summertime, this is the hottest region, and in the winter time, this is the hottest region. And since this is the equators, you see that you get different area which are warmer in different seasons. But that's just because you get this tilt. No tilt, no season. So you may try to compute the Earth temperature here at the Earth surface, and you may do that as a balance between incoming radiation and radiation. So let's say that this is the Earth, and the Earth gets all the radiation that go through this disk, and this disk, which is the same, will be pi r to the square times s. And this is the incoming. And then a fraction r, like albedo, is reflected back. And so that the total amount this input minus that input is the second end pi r square s times 1 minus albedo. And this incoming short-term radiation will be equals to this, which is the infrared radiation from the Earth, heat that escape from the. If you use a Stefan-Boltzmann law, you know that infrared radiation is proportional to a constant, the Stefan-Boltzmann constant, and T to the fourth. Okay, and so you can easily say that from this equation you can compute T of equilibrium. So it will be equal to S divided by 4, 1 minus albedo. And here you get sigma, and then everything is to 1 to the 4. Okay? If you put the proper number, you get something like what? Something like minus 20, I think, degrees freezing. It's very cold. This is not what happens. But then, if you put an atmospheric layer here around the Earth, this is like a cotton. This is like something that keep the heat there, and you get a situation like this. So here you get the external layer. This is the flux of incoming energy. This is reflected back, and this is like in the previous slide, sigma T to the fourth, and if you make a balance here, you get your temperature. But then you can also make a balance here. And in this case, for the layer close to the Earth, you get that this is the input, this is the input, this is the output, and so you get a T, let's call it whatever, T0, and in this case you get the same number as before, minus 20, because the equation is the same, but it pertains to the upper layer of the atmosphere, while in the inner layer close to the Earth's surface, you get something like plus 10 degrees, which is more close to what we are able to observe. So what's the point of this very simple computation? The point is try to illustrate that the planet can be seen as an object, and you can try to make a planetary scale computation of the energy balance and the energy mass, and you may start to understand something of what's going on, even from very simple experimental observation and very simple computation. But you are already starting to think on a planetary scale. In reality, the picture is much more complex because you get different layers, you get clouds that increase the albedo, and then lower clouds behave differently from higher clouds. You will have that something is blocked by clouds, but something escapes through clouds. So the real picture is more complex than this one. However, this very simplified picture already teaches you something. You can understand something even from rough simplification. Good. Now that we have said something about the energy cycling and the energy budget, we can move towards the hydrological cycle. So we saw before, like here, this is the energy budget, and you get something like this. We saw it, and this also drive, here you see it, up rising wind and atmospheric circulation, and so you get movement of energy, but you also get movement of mass, because you get air, winds that move, and this movement also transport energy and mass. One of the major constituents which is moved by winds is water. Water is a very important component of the planet. So this circulation transports energy, but also material. And the most important substance transport is water. As vapor and clouds. And this is very important both for energy and for fresh water distribution. We may easily say that water is the most important component in the planet. It's the most important chemical compound. Because if there is no water, everything else would be very, very different. So it's a blue planet. Most of the planet is covered by water, and Earth is the only place in the universe, the only planet in which you can get water in the 3 different phases. Meaning that you remember maybe this state diagram for water. This is the triple point where you can get solid, liquid, and vapor. Well, this is in normal condition for us. Everyone is able to observe ice, water, and vapor water into our planet. Water is important because it contributes to defining the weather and the climate of the planet. Also, transport of chemical, because most of chemical compounds are dissolved into water, and there are other properties which are very important. Also, within water, we get a number of compounds, and the composition is nearly constant. So let's have a closer look to spatial properties of water. So you get specific heat. Do you remember what specific heat is? It is the amount of energy which is required to increase a kilo of substance of 1 degree. So higher than any solid but ammonia. In order to warm a kilogram of water, you have to provide a pretty large amount of energy. So this implies that you get buffer. This implies that the ocean warms up very slowly. If this specific heat would be much lower, the difference in temperature in ocean between winter and summer will be much higher. Because it will be much faster for the ocean to warm up or to cool down during the winter. Same for fusion. This is not specific heat any longer, this is latent heat. In order to condense from to solidify from water to solid water to ice, it takes quite a lot of energy. This implies that if you have a lake and you are a fisher and you are swimming within the lake, in winter time you have a good possibility that not all of the lake became ice. If the latent heat of fusion would be lower, when the weather becomes cooler, you have a very fast ice formation. And with relatively little energy loss, everything freezes down and became ice. Instead, if the latent heat of fusion is pretty large, it takes quite a lot of energy to form all that ice. Same stuff for evaporation. It takes quite a lot of energy. Warming, in this case, before it was cooling, take energy away. In this case, we are in summer, put energy into your lake. The lake will be there. If the evaporation latent heat would be smaller or much smaller, in summer everything would evaporate and you would have no lakes or smaller lakes. And so, as you see, for life, it will be much tougher. And this property somehow shield the capability of life, buffer the environment, lake and ocean for life. And then you get solvent property. So you may think, if you do not think careful, that water is a very good conductive medium. But if you think again, this is not true. Water is conductive when you get salt dissolved into the water. But if you get pure water, just water, this is a pretty good isolant. The electricity do not pass very easily in water. And indeed, if you get a crystal like sodium chloride, the common salt, this you may see it like this, protons, positive ion of sodium and the number of negative ion of chloride, they are kept together because you get ionic bonds. But then if you have water and you put it there, water is a sort of dipole. So this is oxygen, this is hydrogen, and here you get a sort of negative charge, get a sort of positive charge. So you can visualize a water molecule, something like this, positive water molecule that actually separate sodium from chloride and make the ionic bond weaker. So the salt dissolved and the salt dissolution take place because of the solvent property of water. And this is very important because once these compounds are dissolve in water, at that point you can get chemical reaction. Chemical reaction mostly take course in water solution. They do not take place into solid phase, but in liquid phase. Okay. So we see that it's important. This water is very important. It has very peculiar composition. So if we were in a room, I would say, what would happen if the evaporation heat is smaller? Would the rain be larger or smaller? So same amount. Let's say that you get a lake, you get the energy, you create clouds, and then the clouds produce rain. And the amount of evaporation or clouds would be larger if the evaporation latent heat would be lower, okay? If these were lower, we will get a larger amount of water that is evaporated given the same energy, so we would have more clouds and in due time we will have more rain. And this is what is actually this is not what is actually now we do have lose my grip. We get this water, liquid to gas, and we get water movement, and water circles through space and through phases, solid, liquid, and gas, is the hydrological cycle. It also define what we call hydrosphere, and the hydrosphere, the opposite side, contains all the waters that you get into the earth, and 97% of this water is made by ocean, so it's salty water, and only 3% of the water is fresh water, what you drink. But actually, you cannot drink it because the large fraction of this fresh water is in ice form, in the pole or in the mountain. And so the availability of fresh water for you actually depends on this hydrological cycling. And so here we get some number. Let's say that this is the total water supply, and you get most in the ocean and a much lower fraction, 38 out of more than 1,000 into the ocean, but then you get evaporation In respect to the total amount of the ocean, of course, we have a small fraction that evaporate, but this is fine because we do not want that our ocean totally evaporate. You get rain. You see that over the ocean, the amount of rain is something like 90%, and about 10% go there with winds. You get clouds, you get rain, and then lakes and river, and these close the cycle. And just some amount go into the groundwater, and it also go through seepage into the ocean. So here you get a different representation, but it's the same stuff, same cycle, hope. And a box representation is like this. You may have seen this one, and you may have asked what are the dimensions. So here we get a more precise picture in standard unit. But you see the number are not too far from the previous. Here. So 97% is into the ocean. In atmosphere, you get a very low fraction of the water. This is precipitation, this is evaporation, and this is a sort of a schematic cycle of water. What happened to your water? The vapor can become water and rain through two mechanisms, either because the temperature is dropping or possibly the pressure is lowering, like when you get foam winds, you get mountain, you get water, and you get the winds, and the winds go up to the mountains because there is a mountain. And there you get a lower pressure, and so you get clouds and possibly rain. Or just because it became cooler. The solid earth also is moving. This is the magma, and you get that the crust is like an island moving over the magma waves. And these are the tectonic plates. You have probably seen it in the high school and also in other classes here in ICTP. But also in this case, you get cycling. You may start from, let's say, sedimentary rocks, and then you get that through pressure, your sedimentary rocks became metamorphic rocks and possibly igneous rock. But then you get watering, rain, disrupting the rocks, and all these rocks became again detritus and then sediments. And in geological time, the sediments may become again sedimentary rocks. So you get a number of cycling from water to rocks. And another example of rocks, the cycle, is the carbon, because when you get this cycling, here you get silica, you get carbon, you get aluminium, you get magnesium, and this is all abiotic, no-life cycling. However, when you focus on some element like CO2, on the top of this rock cycling, you also get the biotic cycling. So this was the cycle that we saw before, weathering, sedimentation, and then possibly metamorphosis. And here you get biological cycling, because the CO2 molecules are taken up by plants through the photosynthesis and they are released back to the atmosphere through respiration. So CO2 is going into the trees and out of the trees. And this is a sort of inner cycle in the carbon cycle. So this, let's say, is the slow carbon cycle related to rocks. And here you get a much faster carbon cycling related to life. So this is a cycle that goes on in geological time, and then you get cycling that go on in, let's say, biological time. What else? And these are the equivalent of what we saw before. Before we saw a schema of water cycling. Here you may get a schema of carbon cycling in the rock cycle and in the total cycle. So let's have a look. Here you get sediment. A fraction of this sediment is dissolved and you get carbonate dissolved into the water, and you also get atmospheric CO2 that goes into the water because it dissolves. This is the enredo, and this carbonate is in equilibrium with H2CO3, which has to say water and CO2. And some of this CO2 go back to the atmosphere. But then as part of the carbonate sediment became sedimentary rocks, and then through weathering, rock weathering, or through volcanism, you go back and cross the cycle. Then, if you take this picture and you move on the other picture, you see your primary producer. Those are plants that through photosynthesis take up some of the atmospheric CO2. And here you get herbivores, animals that eat the plant. And so you get a flux of carbon here, which is driven by life component. And then this will be respiration, this will be organisms that die and became again detritus. And the rest of the cycle is more or less the same. We have been talking about Gaia. So the fact that our system is not at the thermodynamical equilibrium. And Jim Lovelock devised a sort of conceptual experiment that was Daisy World. So he said, let's say that you get a planet, and the planet can be the planet and you get a balance, energy temperature, or you may say that white daisy. And when you get reflection and larger the albedo, so the smaller the fraction of energy that warm the planet. So the larger the daisy coverage, the lower the temperature, okay? If you get no daisy, the albedo is pretty low and most of the energy stay on the planet. If you get a very large number of white daisy, the albedo is very large, most of the energy is reflected back to the universe and the temperature became lower. But then you may also say that daisy coverage is a function of temperature, because daisy grow very well in this temperature, but they do not survive if the temperature is too cold or too low. When you combine these two things, you get a feedback effect that basically stabilize the temperature of the planet. So those are this is T and daisy coverage, this is T and daisy coverage, but you can reverse the axis and put them on the same T and daisy coverage, and you see here that, let's say that you are here. If you increase the temperature, what's going to happen? You increase the temperature, and this is cause an increase in daisy coverage. And since you get an increase in daisy coverage, you will also get lower temperature, okay? Because you increase the albedo, you lower the temperature. So this is a feedback that say when you increase the temperature, you get a mechanism that take the temperature low again. And from here, if you decrease the temperature, you would decrease the daisy coverage and the albedo would increase and the planet would warm. Because I lost you for a moment.
Yeah, Prof, the network was very bad, so I think we couldn't hear you.
Okay.
So it went off totally, and you have to go back.
I will go back from where? From Daisy Warder?
Yes.
Yes.
Good. Let me share the screen again. But I mean, it's not a difficult concept. Just take a bit. We are here. Did you get this part? Okay, and this, you get the feedback, no? So we will get over this again. Here you get that when the daisy coverage, the white daisy coverage is increasing, you get a larger albedo. So a large fraction of energy is reflected back into the atmosphere, a lower fraction of energy is kept by the planet, and the temperature decreases. So temperature decreases with the daisy coverage. On the other hand, you get that there is an optimal temperature for daisy grow. Daisy grow very well at this temperature, but they do not survive if the world is too cold or too cold or too hot. Okay? So what's the point? Here, daisy and temperature. Here again, daisy and temperature. When you put this graph, you combine this graph with this other graph, you get something. So you get temperature and daisy coverage. This is one and this is the other. Okay? Here, if you're here, this is temperature. You get an increase in temperature because maybe the sun is becoming hotter. At this point, since temperature increase, also the daisy coverage increase. But if the daisy coverage increase, the albedo increase, and because of the increase in albedo, the temperature goes down. So you get a counteracting effect that dampen the perturbation. On the contrary, if the sun faded and the temperature became a bit cooler, you move from here to there, and then you decrease the coverage in daisy. And if you decrease the coverage in daisy, you decrease the albedo, and the planet warm up more easily. And so you get a counteracting effect that bring the temperature back. So in all of this region, from here to there, you get, because of the presence of daisy, a negative feedback that stabilizes the temperature of the planet. And this is because this is negative, and this is temperature increase, daisy coverage, temperature increase, daisy coverage increase. So this is like this. They have different size, and so this is a negative feedback. To there, you get a positive feedback that amplifies all the situation, all the perturbation. And so the bottom line is that if you get a planet with no daisy at all, a bare planet, and you increase the energy from sun, you will get that the temperature of the planet would increase proportionally to the energy flux. However, if in the planet there are these white daisy, there are some situation, time, temperature interval in which the temperature is stabilized. And what Lovelock was trying to prove with this is that the presence of life may create a feedback mechanism that stabilize the condition of the planet and make it more suitable for life. But the important point is that feedback mechanism may introduce a non-linear effect that may produce some counterintuitive situation. Like in this case, you increase the energy from sun, but in spite of the energy budget that we saw before, the energy budget, this one, in spite of stuff, you get that the energy increase, but as the energy increase, also the fraction of reflected energy increase, and the temperature stay the same within given limits. And then you go back to the normal situation. So in principle, this is what I was meant to show you last time, but now we can go back to what I may try to show you this time. Which is a closer look to this hydrosphere. So in part, the concepts are the same. We just saw this, and also this. This is the rock cycle. This is the magma, volcanic. Okay, this is the hydrological cycle. And so now we go a little deeper into the salt composition, right? So this is something that different color, good, definitely away. Salt, every society, sooner or later you get a picture like this and you get salt from the ocean, just from evaporation. So one possibility to understand what's dissolved into the ocean is just to make the ocean evaporate, and then you get about 3% in weight of solid. And this solid in reality is not just sodium chloride, which is what most of us think, but you get something like 54 different salt components. If you try to make your own evaporation at home, the first stuff that you produce in the bottom of your beaker is calcium carbonate, then you get gypsum, then you get common salt, and then you get other compounds. However, it's not very easy to do this stuff, because when you make your evaporation, you may strip out a number of salt that are lost in the vapor phase. But given some tricks, if you pay attention to the problem, you have the possibility to make a pretty accurate measurement. And this is what Sir Dietmar made already a century ago. You may remember the Challenger, that was a ship, the same one in which Darwin was making his observation a century ago. And Dietmar, he analyzed water samples in this way for many different locations. And what he understood? He understood that we get a fixed proportion of different salt compounds regardless the position of the sampling. So you take a glass of ocean water into the Atlantic Ocean, you take a glass of ocean water in the Pacific Ocean, or in the Mediterranean Sea, and the composition is roughly constant. It's not perfectly constant, but it's very similar, at least insofar major constituents are considered. And indeed, using this idea, one may think that the total amount of salt is proportional to the concentration of chloride. So one way to measure salinity was to measure the chloride component and say, well, the total salinity is the chloride concentration times 1.8. Another possibility is to make a conductivity measure. The higher the conductivity, the higher the amount of salt dissolved in the water. And you do that with standard, what's the name? Lawson bridge, I think. You get a circuit like this, and here you get an instrument to measure the passage of current, and here you put your salt. And you can adjust the different resistors and get the equilibrium situation, and from that you measure the conductivity and you infer the salinity content into your water. Just checking if you're all there sleeping, maybe. And then this is the element that you may get into the water. As you see, there are many. You're familiar with chlorine, you're familiar with sodium, magnesium, sulfur, and this is a decreasing abundance into the water. And you may say that here, major elements, if you get more than 1 millimole per kilogram, then you are a major element. So in the ocean we got carbon, potassium, calcium, sulfur, magnesium, sodium, and chlorine. They are the major constituents. Those major constituents are the constituents that are in a fixed proportion. And then you get a minor element up to here. So this was 1 millimole, and this is a billion of a mole. Do you know what a mole is? Make a note or say something. Do you know what a mole is? No? Yes? Yes? Someone say yes. Someone say no. Is anyone that does not know what a mole is? Mind you, the examination may have this mole concept. So if you know it, it's fine. If you do not know it, it's a good idea to say it so that we can revise it.
I don't know, sir.
Good. Why did you tell us before? So a mole is a very specific measure. You may say that if you get, there is a very specific number which is called Avogadro number, which is 60 times 10^23. Okay. Whenever you get an Avogadro number of object, you get a mole of this object. So if you get 6.023 times 10 up to the 23 of this pencil, you get a mole of this pencil. Take protons. hydrogen plus. If you get a mole of hydrogen's proton, which means 6.023 times 10 to the 23 protons, you get a mole of protons, which is a mole of hydrogen also, because the electron doesn't weigh anything. This mole of hydrogen, which is equal to the mole, sorry, I will silence my legs is getting down. There, I was saying the mole of hydrogen weight 1 gram. Okay? So, if you take 1 gram of hydrogen, considering that electron doesn't weigh, you get 6, an Avogadro number of hydrogens. And you call it 1 mole. If you get 1 mole of oxygen atoms, then this implies that you get an Avogadro number of oxygen atoms, and when you put it on a balance, it weighs 16 grams. Well, sorry, 8 grams. 16 grams. Okay, so this is the atomic weight. This is the atomic weight, and the relationship between atomic weight and atomic number, the weight on the balance, and the atomic number is the Avogadro number. And the Avogadro number is the element that defines the mole. So, this is a measure of concentration. So this implies that major constituents are ordered 10 to the 20 molecules per liter. 10 to the 70 molecule per liter, a smaller amount, trace element. Trace constituents, there are very, very few. Here you get a pictorial representation meant to fix your mind that most of this is water. Then you get major constituent like this, minor constituents and trace. Now, minor constituent is just this thin stuff, and trace constituents is an even thinner component, the blue. Okay. However, even if you get more or less fixed composition, if you take observation all over the world, you see that there are spatial differences in the concentration of salt. Here you get a representation, and you see here you get a maximum 36, those are isoline of salt. Here you get 37, but there are regions you have to get 35, 34, 32, and the same is, this is a vertical section, okay? And actually this is the section, this is a transect, and this is a point, this is point B, this is point A, and these are the profile for point A and point B. So, which is this one? A or B? We start at 36 and something. So here we are between 36 and 36.5. But then when you go down in depth, you have a decrease up to 34, and then a small increase. here you start from 36, you go down, but then you get this increase, and then you go down. So if you look at this line in the graph, this graph, you see that here you get this small increase, which is this bump. So this is profile B, and this is profile A, okay? So this is the constancy of composition of typical exercise. What's the concentration of potassium if the total salinity drop to 32? So normal salinity is 34. If the salinity would be lower because there is a lot of rain and fresh water, whatever, given then this composition is constant, what would be the potassium concentration? So potassium is here, so 48 over 34,482 times 32. Okay, easy, straightforward, isn't it? Good. Look, negative ions by weight is 21%. Positive ions by weight is 12%. Is this possible? It is, because some of the ions are positive or double positive or negative or double negative. So the total solution will be neutral, no charge, even if by weight the negative ions are more heavy than the positive ions, because this is weight and there's no charge. Where does the salt came from? This is, let's see, dissolved component. This is air. And this is water. So we may say this is the ocean, and we say that, you remember, the earth was formed, we said it last time, and then we get cooling, and the water vapor condense, you get a massive rain, and you get the ocean. But at that moment, your ocean is just water. There is no salt. And then some substances somehow end up into the ocean. So we may say you get molecules of oxygen, they go down. You get molecules of CO2, they dissolve into the water, and or whatever, doesn't matter the name. You get gas dissolved into the water. However, if this is the concentration in air, you see that the concentration in water is in different ratio. So this is nitrogen, oxygen, argon. Argon is much smaller, the concentration of argon in water, than in the air. On the contrary, gas, CO2 is much more present into the water than in the atmosphere. And here the ratio also is different. So this may be 5, this may be 3, 10 and 10. So This solution is a component but does not explain the whole story. Let's take a different approach. Maybe we get a link between the river composition and the ocean composition. And so let's say this is rain, this is a river, and this is seawater, ocean. Now maybe it's a bit pale, but here this is sodium and potassium in rainwater. And this is sodium and potassium in river. And this sodium and potassium in the ocean. And so you see that there are changes from the rain to the river to the ocean. So it's not just this solution and take the element from the atmosphere and put it into the ocean. And this is true also for calcium chloride in the atmosphere, but when you go into the river, calcium chloride. And when you go to the ocean, calcium chloride. So you have differences. Not only this is 15 order of magnitude, this is 250 magnification. So this is 460 thousandths. So it's not just a physical component. You get concentration, you move from 460 thousandths and you get a different ratio in your composition. And you see that river waters, this is river, is mainly calcium and carbonate. This is carbonate, the larger number. And this is calcium, the larger negative number and the larger positive number. While in seawater, you get mainly chloride, the largest negative number, and sodium, the largest positive number. So it's totally different. And in time, different scientists propose a different explanation for this. And basically, it's a combination of everything. So one possibility is weathering of rocks. Weathering is you get rain, possibly acid rain. If you get volcanoes, you get acid rain. And this rain react with rocks and you get a dissolution of bicarbonate. Whenever you say that all the rocks dissolved completely, you get a congruent reaction. If you get that part of rocks dissolve and leaves a different kind of rocks plus some dissolved substances, in this case you have an incongruent reaction. And in this case, the concentration of the remaining rocks, part of the rocks dissolved, but totally. What is left in the solid phase has the same composition. In this case, the composition change. You get a different rock. And this complex picture, you can just look at the orange stripes to begin with. You get rock plus rainwater, and you get a dissolution of some element and a different rock. So this is an incongruent dissolution. You start from aluminium silicate, which is most of the crust, and you get a different type of aluminium silicate, and you release in the solution some chemical compound. And then these chemical compound have some equilibration, because when you get into the water, you get chemical reaction and you get a different rock, you get precipitation of calcium carbonate. So some components became solid, they go down, some others stay up. And you also get biotic relationships. You get that some marine organisms, they grow shells, and the shells of clams, corals, is calcium carbonate. So these remove calcium. Then you get volcanism that release chloride, and this changes somehow the composition of your water, and the net effect is that you get more chloride, less calcium, and so an enrichment in sodium chloride. These also take some composition. Following this line of reasoning, there was a chemist, Silent, that say, let's assume that you get this compound, water chloride, water carbonate, and these phases, different rocks and water. Let's treat everything as a chemical mixture, and let's compute the thermodynamical equilibrium. So this was very complex, and this is meant to drive you in the computation of the chemical equilibrium. We will not get into this detail, and that because it didn't work. So he tried to do this, but then this is the moment it didn't work. He tried to make some comparison between observation and reality, and it didn't work. So the thermodynamical approach, and say we have these components, these rocks, this water, compute the chemical composition, is not enough. Again, you get rocks, different kind of rocks, you put water, you get differential dissolution, and you compute the chemical equilibrium. This is not enough to explain the composition of the ocean. And so you want to go towards a different approach, which is not the thermodynamical approach, this one, sediment in equilibrium with ocean, but is something more. You want to follow a kinetic model. Also because this implies that you are equilibrium, and maybe we are not at equilibrium. So we saw a bit of this, and we also saw something of this. They all contribute in defining the composition of the ocean. None of it is enough. And so let's take a mass balance approach. Let's say that this is the ocean. You will have an input, and the input may be rivers, maybe ridges, maybe others like aerosol, and you also get sinks, something that take out the salt from the environment, from the ocean. And here you get a pictorial representation of this. You may have volcanoes, you may have ridges, you may have sedimentation, and you may try to run a budget for all this stuff. And now we try to do that. So let's say this is the ocean. We call it volume of the ocean and concentration of the ocean with reference to a given chemical compound. The input rate yeah, is equal to the product of the concentration in the river times the volume of the river. So you may get that rivers flowing into the ocean take a given amount of liter per second, and you get sodium concentration equals to sea river. So this would be liter by year time grams of oxygen time liter, volume time concentration, and this is an input. Okay, so this is an equation, time derivative of C, this one, is equal to the input. Okay, so the time derivative of the concentration of an element in my ocean is equal to the input. I start from 0, and then this will increase proportionally to the input. And this is a time scale for the velocity of increase. Now, if you make your computation, you see that the time scale to reach the present concentration, you get a number like this, which is like this when you put figures for the volume of the ocean. This is the volume of the ocean. This is the volume of river. And so you get that the time scale to reach the present concentration of a given element is like this. And this is the ratio concentration in the ocean and in the river. And now here you get the table. This is the ocean concentration and this is the river concentration that you can put there in order to compute tau, the time scale. Here you see tau changes order of magnitudes. We get huge difference because if you focus on bromine, it would take 120 billions of years to reach the present day concentration. If you focus on silicon, 50,000 years will be enough. So if you regard this as the age of the ocean, well, the age of the ocean changes depending on the element that you are focusing on. Not only, even if you consider the slow filling element, the ocean should be not very old. So this does not work. This is not all the story. We have to make it more complex. We need to have some mechanism in place in agreement which it takes a longer amount of time to reach the equilibrium concentration. So we will get input like before, but we also get losses. So that we lose something, and in order to reach the present day concentration, it takes a longer amount of time. So the new differential equation is this one. And in this case, we may have you can compute a steady state, but you can also say that your loss, let's make a first order approximation. We say that this is time, this is the amount of a given substance into the ocean, ocean volume time ocean concentration of whatever. And we say K time this is a fixed proportion, like 1%, or maybe 0.1% of the present day concentration is lost. So these are the losses. First order approximation, fixed proportion is lost. And with this assumption, we can integrate this differential equation, and we have this steady state solution. And again, tau is a time scale that tells us how long it takes for a substance to accumulate into the ocean. And in this case, the situation is much closer to reality. We will go back to that in a moment. This is a Mendeleev table. You've seen it in the high school. So you get hydrogen, lithium, magnesium, titanium, aluminium, and so on and so forth. And here, rather than the element, you also get the vertical profile. So you see that for this element, beryllium, this is surface of the ocean, you go down like this. This is a constant. This is a constant. This increase and then decrease. You get different profile. This is a zoom. And you see this is carbon, this is nitrogen, this is lead, this is mercury, this is potassium, sodium, and magnesium. And so we see that some elements do not vary. They are the major constituent. So this implies that mixing, vertical mixing time scale is faster than the input from the river and removal mechanism that we saw here. Because those mechanisms of input and losses would create some differences. But if the vertical mixing is fast enough, they are constant. This is true for sodium, magnesium, potassium. And then you get that in other cases you have that those mechanisms of removal and input change the vertical distribution. And this is when the vertical distribution is not fast enough to cope with this mechanism. So this may be the case of lead. Increases the surface. So that's a hint that you get anthropogenic pollution from the atmosphere. And indeed, this is the case for lead and also for mercury. And then you get cases like phosphorus and nitrogen in which you get an increase in the surface. So in respect to, let's say, a constant situation, here you get some process that take nitrogen away. Some uptake of phosphorus and nitrogen. And these are life. These are plants, like phytoplankton, that lives just in the surface and take up the nitrogen and the phosphorus. So this is biological activities. So you get that you may have some bio element, and we will focus on that in one of the next lessons, because they are the carbon, nitrogen, phosphorus, silicate cycling that we want to focus on. These are of interest if we work with pollution, and these are of interest if you do not care about life, but just a geochemical cycle. So not biogeochemical cycle, but geochemical cycle. Okay. You know, I didn't figure out how to see all of you. I can see just 4 pictures, so I keep switching from 4 of you to other 4 of you. I have to press a small arrow just to look from your face whether you are totally lost or you're following. But it seems that you're following almost. One more slide. This is the vertical structure of the biogenic compound we just mentioned. Okay, so you get like nitrogen or phosphorus or carbon. You get photosynthesis, meaning that you get a very tiny organism, diatoms, coccoliths, that take light, make photosynthesis, and get this material and transform it into organic matter. This takes place just in the upper part of the ocean. And so if you get a profile, it will be like this. This is depth, this is surface, and this is the carbon profile, because here I take up the carbon. And then when you get sinking of material, dead material, maybe into the bottom of the ocean, you get bacteria that process this organic matter and transform it again into inorganic matter. So maybe here you may have something like this, a release of nitrogen and phosphorus. And this is a typical profile. So I think that now we are over with time, but next time we will try to make a simple toolbox computation of fluxes between ocean surface and deep ocean for a generic tracer C. So next time we start from here, and since I will put into the folder this material, if you want, you can have a look this few slides to make this computation in advance. Should be easy to understand for most of you. Otherwise, you just enjoy Barcolana. We will see on Monday, and I will go through these slides together with you. Good. Any questions, or we just see on Monday? Okay. So have a nice weekend, and see.
Sir.
Yes.
Just a suggestion for next time.
Yes.
In your desk there is a lot of echo sounds, so the sound is not that good.
Use your sort of echo.
Yeah, there is a sort of echo in your desk, so in your office. So for next time, if it's possible to manage it, because the sound is not that good.
Well, I understand that, but that's difficult for me because I didn't hear any echo. All of you hear the echo? Or is it just you? What about the other students? Do you also hear some echo?
I think it's the network. At times it fluctuates.
Yeah, the network was very bad, and sometimes it would just cut off and.
Okay, so maybe it's because network.
Look, if you prefer that, are all of you in Trieste?
Yeah, no.
Only one person.
Only one person is not in Trieste.
Well, if you prefer that, we can meet in person. I mean, now, in this precise moment, I am in the ICTP campus.
Yeah, it will be better,
I think. Very nice.
You prefer that? I think that usually you go into these Stasi rooms. Is it right?
Yeah.
Yes.
Okay, so I will ask Patricia to book the room for us, so that next time we meet in person.
Okay,
And we
great.
get rid of this eco stuff.
Okay, thank you.
Thank you.
Thank you.
Thank you, Shu.
Thank you.
Thank you, sir.
Bye.
Yes, sir.
Goodbye.
Ciao.